Here we are for question 3 of the 2019 chemistry exam. And looking at this, I can see an equilibrium sign here. I can also look at this and I can see a graph. So it kind of looks like rates of reaction and equilibrium to me. Let's get stuck into it and have a look at it. So the cobalt, this dude here dissociates to that, and we've got blue and pink. So therefore we've got a mixture of bluey pink color. We've got equilibrium mixtures are heated to 2 different temperatures, and I'm guessing this is the amount of stuff we have. The intensity of the pink color is that. So this here is our pink color, and it's recorded over 30 seconds, measuring the absorbance, blah, 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 blah. So therefore, this thing here is based on the CO2 positive stuff that we have. And it looks like there's more of it at a lower temperature, which I'm guessing is going to be important for our question. State whether the forward reaction is exothermic or endothermic and justify your response by referring to the graph. Okay, so let's just first of all go with referring to the graph. So let's refer to what the graph says. And it says at a lower temperature, there is a greater intensity recorded, which means more CO2 positive is produced. All right, so a lower temperature, we've got more of that. So therefore, this means the forward, because obviously this here is our pink color here, so we've got more of this at a lower temperature. So the forward reaction's favored. The forward reaction is favored. This suggests the forward reaction is exothermic. So anytime you get a greater yield at a low temperature, it's because it's exothermic, because the reaction is trying to oppose that and favour the forward reaction. So that's basically Le Chatelier's principle applied. So therefore the forward reaction is exothermic. Highlight the fact that I want them to look at that, and then know that the lower temperature, that's my explanation, which is fair enough. And I refer to the graph as well, stating what the graph is showing me. Pretty much exactly what the graph actually says. Next, part B, when 5 mils of water is added to the equilibrium mixture, so we're diluting it. So a dilution here, I'm going to do a dilution. The color of the solution immediately became lighter pink. Well, it makes sense because we diluted. Describe the final color once equilibrium is re-established. So let's have a look at what's happening here. If I dilute it, dilute means we favor the side with more particles. Therefore, the forward reaction has got more particles. So I'm going to first of all state the basic what's going to happen when I dilute it. So add H2O will favor the forward reaction as it has more particles. Based on Le Chatelier's principle. All right, so therefore, what does that mean? Thus, more pink color is produced. More pink color is produced. So the color will lie, so it will be between the initial dark pink and the light pink after dilution. So basically the scale of it, you're going to say that the pink will be darker than it was originally, but lighter than it was immediately after we added it. So therefore that pink lies there. So if you're thinking about our pink color on a graph here, what's going to happen is we have it at equilibrium. We're going to add our water, which is going to decrease its concentration. It's going to favor the forward reaction to produce a bit more pink color. So therefore, you can see here that this is it at the end. Pink color at the end. So it lies between our darker pink and our lighter pink. It's somewhere in between there. And I tried to get that across in my response here to say that whereabouts on the pink scale it will lie. So not just a lighter or a darker, but where is it in comparison to these two pink colours that we've talked about before. Anyway, let's move on to part C. We are adding 5 drops of silver nitrate. Silver nitrate, what does it do? It reacts with chlorine, reacts with Cl negative to produce a precipitate. So we add that at time t. A concentration graph for this is shown here. So what's going to happen here? So basically with any graph like this, we got 3 parts to it. We've got the initial change, the Le Chatelier change, and the re-establishing equilibrium. So what's going to happen if I add silver nitrate, instinctively my chlorine is going to drop dramatically. That's because my silver nitrate is going to react with my chlorine in my system. Then Le Chatelier says that the reaction is going to partially oppose that change. So let's have a look at what it's going to do. So if we've dropped this, it's going to favour the Ford reaction to reproduce some of that. Now, the ratio here is 1 to 1 to 4. So I need to make sure that when I show my Le Chatelier change, that I'm going to produce 4 times as much chlorine as I am the cobalt positive, 2 positive, and obviously this is going to decrease in the same amount of that. So let me go back here. And I'm going to say that my chlorine is going to go up 4 spaces. So it's going to go up 1, 2, 3, 4, and then reach equilibrium. Okay, just like that. So that's the Le Chatelier says we're going to partially oppose our change. So it's going to go up and then reach equilibrium. What's going up with it? What was it again? Going up with it will be my cobalt. So therefore, this is going to go up by a quarter of that. So this is going to just go up by 1 line. Again, that ratio is important to identify. It's going to go up by 1 line. I'm going to show that I'm reaching equilibrium around that at the same time here. And then this is going to go down by about 1 line. So where's equilibrium going to reach here? It's going to show that it's going to go down here, reach equilibrium, and then stay at equilibrium here. So therefore, that's what's going to happen to my changes. Now, this is a bit hard doing just 1 line here. So if I did this again, I'll probably go down a fair bit and up 8 lines, and this would go down 2 lines, just to get that ratio. I might identify this as being X, this as being 4X, and this as being X as well, to show that I know my ratio is there. But that is going to be what's going to happen there. The 3 marks, again, 1 for our initial change, 1 for our Le Chatelier change, our curvatures, and then 1 for where we're going to be re-establishing equilibrium at the same point in time, and the ratio being right there. So 3 marks. That is